So let's look at an example, start to finish, of what you'll be doing with these sampling distributions of proportions. So again, with these, in the wording of the problem, you'll want to look for your population proportion and your sample size. So that'll be given to you. A piece you'll often need also is that if they give you P, Q will be helpful for when you get to checking the conditions. So once you find what's given, then you'll want to check the central limit theorem. So CLT for short. So checking the central limit theorem, you'll want to make sure you have independence, which again, you'll just write down and check. Same thing with randomization. Just write it down and check next to it. But then success failure will show a little work to show that we do have large enough sample sizes. So taking sample size times P, making sure that's more than or equal to 10, sample size times Q, making sure that's more than or equal to 10. And then once you have that, then we can start to build our bell-shaped curve, and you can define your parameters. So your parameters, you'll have your mean, which is just going to be equal to your population proportion, and then standard deviation, which will be square root P times Q over N. And then once we have those parameters, we can start answering questions with the bell-shaped curve. All right, so there's a lot of setup to it, but it ends up being questions similar to what we did in the previous module. So we have information on packet of seeds, claims that the germination rate is 92%, and there are approximately 160 seeds in each packet. So what we're dealing with here is population proportion is the expected germination rate. So we expect 92% of the seeds to germinate. And if you have P, you might as well write Q down because that'll be helpful in our central limit theorem. So 1 minus the 0.92, which is a 0.08. And then we're going to be looking at a packet of seeds, so sample size of 160. So discuss each of the conditions required to use a sampling distribution for the proportion of seeds that will germinate. So our conditions, that's going to be our central limit theorem. So independence, actually, I'll just go through and write down what I expect of you, and then I'll describe independence and randomization a bit further, just so you understand it. But what you'll be doing, independence, we'll just assume both of those are good. And then success failure, what we'll do is take N times P. So we're going to take 160 times 0.92. We'll also take 160 times Q, which is a 0.08. And I'll just see what those values are. So success 147 and then failure 13. And both of those are more than or equal to 10. So we're all good to go. Independence, we could say something like sampling 160 seeds out of all of the seeds. It's less than 10%, so it would be independent of how the behavior. Randomization, it doesn't say exactly that it's random. It'd be best if they said they were selecting like a random packet of seeds or a random 160 seeds. That would be best. We'll just assume that we have those. All right, define the sampling distribution model and its parameters. So the parameters, we'll need the mean and standard deviation. So for the mean, we'll just copy down our population proportion. It's the idea that we expect this 0.92, that's the center of our distribution. Standard deviation, we'll take the square root of P times Q over N, which is 160. And we'll just take that to 4 decimal places. And then with that, we can define our model in that it's going to be normally distributed with a mean of 0.92, standard deviation of 0.0214. So at that point, we could go ahead to GeoGebra and start to see what our model looks like. We have a 0.92 and a 0.0214. And something to keep in mind in this section, and it's going to come through in confidence intervals and hypothesis tests as well, we're dealing with proportions here, which are percentages, so you should be stuck between 0 and 1 here. I mean, you could see we kind of go beyond 1 on the right-hand side here, and that's fine because those outcomes are extremely unlikely, basically impossible for what we're trying to accomplish, but that's why these values coming through are so small. Your mean should always be between 0 and 1, and then you should have a small standard deviation, because what this really brings through is a standard deviation of 2.14%. So it's like we expect 92%, and on average that'll deviate by about 2.14%. All right, so we can get an idea of what we expect for our samples, and especially in terms of if we have a packet of 160 seeds, what do we expect to occur for the germination rate? We expect 92% to germinate, but maybe we see 96%. That's not totally unlikely, or 87%. But then we could start to get an idea of what's not likely to occur. Like 100% germination, pretty much impossible. All right, so sketch and label a model. So we're going to have a bell-shaped curve. At the center, we'll have a 0.92, and then I'll just go to standard deviations above, to standard deviations below. Adding on that 0.0214, so 0.9414, 0.9628, and then 0.8986, 0.8772. So in terms of this number line, what this number line represents is the percent of 160 seeds that germinate. And it's just that we get this idea of probability coming through with 92% being the most expected, and then we can get an idea of what's usual and what's unusual, going beyond those 2 standard deviations away from the mean. So, what is the probability that more than 95% of the seeds will germinate? So something we need to be careful of here is that typically, or at least before when we worked with normal distributions, when we saw a percentage, we kind of got used to thinking of that as area under the curve, but the area under the curve is the idea of a probability, and this isn't a probability. This right here is 95% of the seeds, of the 160 seeds. So what that's linking to is a number that could land on this number line here. So they're describing a possible sample proportion here. So you take 160 seeds, what's the probability of seeing 95% or more? So what we're doing here is we're looking at our number line, and we want to see where do we land at 0.95, which is somewhere about there. And what we want to find is what is the probability of more than that. So we're going to use this bell-shaped curve, and we're going to look for area under the curve to find this probability of x being more than or equal to 0.95. So I have my mean and standard deviation in GeoGebra already. I'm going to be doing area to the right, and we're going to make that a 0.95. And that's going to be a small probability of 0.0805. So what this would translate to is there is an 8.05% chance that more than 95% of the seeds, even better at saying like 95% of the 160 seeds, throwing the sample size in there, because this is specific to a sample size of 160. If I switched this to like half of a packet of seeds, so 80 seeds, then these probabilities would all change. So seeds will germinate. All right. Then this last question, would it be unusual for only 140 or fewer of the 160 seeds to germinate? So with this the 140 that they're giving us here, that 140 doesn't match up with that number line there. That doesn't translate. So what I'm being told here is the number of successes. It's not the proportion of successes that we're looking for. So what we need to do here is make a little change to it. The idea being, like this part D here, another way I could have phrased this is, what is the probability that more than, and what I could have done instead of saying a percentage is, if you take 0.95 times 160, which is 152, so I could have phrased this as, what is the probability that more than 152 of the seeds will germinate? And it's the same exact question. What's key though in developing our sampling distribution of proportions is how, let's see, germinate. Sorry, I was talking and writing at the same time. Germinate. All right, so right there is this difference of saying 152 of the 160 versus 95% of the 160. But what's key is this limitation of our number line. And so we're limited with this setup of the distribution that we can only plug in percentages here. So with that, we need this 95% form. So here, since they didn't give us the percentage form, what we can do is some work at the beginning to figure out what is this sample proportion. So 140 of 160, and that would be a 0.875. So what they could have done is say, would it be unusual for only 87.5% or fewer of the 160 seeds to germinate? And it's the same question. So what we're going to do here is, we could find probability. What you can also do here is they just want to know if it's unusual, which links to being more than 2 standard deviations away from the mean. So we just want to see, where does 0.875 land in all of this? And what we could see is it's out here to the left-hand side, and it is more than 2 standard deviations away. So you could use that as reasoning. We could say, yes, because it is more than 2 standard deviations away from the mean. You could also look at probability, in that we could have looked at what's the probability of seeing 0.875 or less. So going to GeoGebra and doing a left-sided and then plugging in 0.875, which is a 0.0177. So less than 2% chance of occurring. So that's pretty rare. So you could have also done this by finding the probability being less than or equal to 0.875, which is a 0.0177, or a 1.77% chance. And that also shows that it's unusual. So we could go, yes, it has a very low probability. Or you can make a sentence describing that probability, and because it's low would make it unusual. So those are the types of questions we can answer with our sampling distribution of proportions.